So here we go, 4.6 graphs of other trig functions. So one of the things I gave you to make things move a little bit faster, because we did this for the sine and the cosine function, is I gave you the values in the t-table. So I've got the unit circle over there on the wall. So you can just confirm that if you go to 0 radians, we're measuring in radians, the tangent would be sine over cosine, so we're looking at 0 over 1, so that would be 0. Pi over 4, the tangent is 1, and then pi over 2, the tangent is undefined, because you'd be up at like where the 90 degrees is, and 1 divided by 0, remember, is undefined. So let's plot these points. So we got a point at the origin, 0, 0. All right, I've got my points plotted. Let's also consider, even though it's not on the table, let's consider if I were to go to negative pi over 4, and you can visualize it on the circle. If I were to go to negative pi over 4, what's the tangent? Negative 1. And if I were to go to negative pi over 2, we have another asymptote, would be undefined. And then that would be negative 3 pi over 4. What's the tangent? 1. And then at negative pi. And so when you connect the dots, it's going to have some curvature to it, and you can confirm this by graphing it in your calculator. And then it will go up and approach those asymptotes there, so I'd put arrows on the end of it. So a few things. Now I didn't leave this in your notes, but there should be some space like around in the margin. The period is going to be the distance between consecutive asymptotes. So that's your period. Yeah, it's pi. The period is going to be pi, and this is the distance between consecutive. Now what do we think about the amplitude? Yeah, infinite. I mean, really, it's just not defined, undefined, because it does not. Remember, the amplitude was like for the sine and the cosine. How high does it go from its axis up to its maximum? But since these go up and down forever, there is no amplitude. But you could have a function that was like y equals 3 tangent of theta, and what do you think that 3 would make the graph do? You can't say it changes the amplitude because there's no amplitude. And so what do we call that? How would we describe a vertical stretch? So you could have a vertical stretch. You don't need to write that down. And similarly, if we had something like a third times tangent of theta, that would be a what? That would be a vertical shrink. So you can change the graph vertically. You can stretch it or shrink it. We just don't have an amplitude. All right. Next up, let's do the cosine function. I'm going to give you some time to plot the points and see if you can figure out the whole look of it. Say again? The cotangent function. And of course, like the tangent function, you've also got the period between consecutive asymptotes, so it's again just pi. So let's discuss some of the differences and similarities between the tangent function and the cotangent function. What do you think? What do you notice? A reflection in the x-axis, okay. So you've got like this one is like an increasing. Each little branch is increasing, and then here each one is decreasing. What else? Reflection. Yeah, I guess you could consider a reflection of the y-axis, sure. I mean, not exactly, because like this one is passing through the origin, and this one has an asymptote on the origin. So it's sort of like, I mean, like the main thing is that you've got the increasing, and then you've got the decreasing, and also there's a shift, because here you have asymptotes at negative pi over 2, pi over 2, 3 pi over 2. Where would the next asymptote be, by the way?
3 pi? Oh, wait a second.
Pi over 2, 3 pi over 2, 5 pi over 2, and so on. And here you've got asymptotes at 0, pi, 2 pi. The next asymptote would be at 3 pi, and so on. So the way I remember these is I think about the tangent function, because it's increasing, that's like a positive idea. I mean, it's increasing. The cotangent function is decreasing, so it's like negative. So it's sort of like having a captain and a co-captain on a team. Like the co-captain is really just like a loser, right? So they're negative. It's a bad idea. You don't want to be the co-captain. You want to be the captain. Okay, so co is like negative and down, and then the captain is the positive and up one, yeah? So that's how I remember. Okay. Yeah, you're welcome. All right, so let's go to this chart, and let's fill out some of the basic characteristics of the tangent and the cotangent curve. What do we think about the, let me see, the domain is kind of tricky. Yeah, let's just start with the domain because it's tricky. So we're looking at like the tangent curve. What do we think about the domain?
It's like it's repeating. It goes on forever, but only in certain increments.
Right. So remember when we did rational functions before, we talked about the domain was like you have to jump over your vertical asymptotes. Well, we have a bunch of vertical asymptotes, and there's even more that are not even shown here. So let's think about a pattern that we can say about the vertical asymptotes. So we have an asymptote at negative pi over 2, pi over 2, 3 pi over 2. The next one would be at 5 pi over 2, and then
pi over 2.
Okay, what's the distance between the asymptotes? Pi. So would it make sense to say that the domain, I'm going to have to write small because we're going to say like all real numbers not equal to pi over 2 plus n pi. I guess I didn't need to write that small. Pi over 2 plus n pi. And it's not always explicitly stated, but n, where n is an integer. And we saw this before. I don't know if you remember when we were doing like the sine and cosine function and talking about where the x-intercepts were, because they were happening at regular intervals. And so again, if n is an integer, you can pick any integer that you want, like 0. If you plug in 0 for n, that entire expression would be what? Pi over 2. So that means that we can't be equal to pi over 2, so that works. If I were to pick 5 for n, that whole expression would be,
What?
If I were to plug in 5 for n,
5 pi over.
mm-mm.
11 pi over 2.
Yeah, you
Oh
got
my gosh.
5 pi plus a half a pi. So that's 11 pi over 2, right? 11 halves. And would it make sense that if you were to keep going, pi over 2, 3 pi over 2, 5 pi over 2, eventually you get to 11 pi over 2? Okay, so that's that. Let's talk about the cotangent one. So the cotangent one, we have asymptotes at negative pi, 0, pi, 2 pi. So what can we say for the domain for the cotangent function?
0 plus pi.
Which is
In pi.
Yeah, we can just say n pi, right? All real numbers not equal to n pi. I mean, technically, you might say all real numbers x where x is not equal to n pi. But I'm not going to be that picky. I'm mostly concerned about that expression, like whether it's n pi or pi over 2 plus n pi. And later we'll see things like it might be pi over 2. Of course, if you transform the graph, it could be like pi plus 3 pi over 4n, something like that. Okay, let's talk about the x-intercepts. Let's go to the tangent one first. So we have intersecting at 0, at pi, at 2 pi. What's the pattern? N pi. So we can say that our x-intercepts are at n pi, comma 0. Pi n or n pi, doesn't really matter the order that you go. What about the cotangent function?
0, pi over 2 plus n pi.
Yeah. Well, the 0 is the second coordinate. So pi over 2
Oh.
plus n pi, comma 0. I gave you the intercepts. There is no, the y-intercept. There's no y-intercept for the mother function cotangent curve. And then the tangent curve intersects at the origin. Vertical asymptotes. You already did that, basically, right? Because we were saying that the domain is everything except where your asymptotes are. So for our asymptotes, we can just say where x equals pi over 2 plus n pi. And then for the cotangent function, we're
0 plus n pi.
I like that. That was so aggressive. All right. And then already gave you that they're odd functions. We talked about that before, and so they both have symmetry about the origin. So you can visualize if you were to rotate this graph. Oh, we can actually do it. Rotate this graph 180 degrees. We'd get that, which is the same.
What?
Same thing here. If we were to take this graph and rotate it 180 degrees, we get the exact same graph. So they have symmetry about the origin. All right, let's do a little bit of analysis of this graph. Wait, is there another chart in your notes
Yeah.
about how to graph the tangent and cotangent?
Yeah.
Oh, okay, let's do that first.
Probably.
This one?
Yep.
Okay. So if we want to graph the tangent or the cotangent curve, the first thing you're going to do is you're going to find the vertical asymptotes. And those are going to be like we're still going to do 5 key points. So those will be the first and the fifth coordinates of your table. Then you'll go halfway between, like we did, and halfway between your asymptotes is always going to be an intercept. Now, of course, if you shift the graph up and down, then there won't be an intercept. But you'll notice we're not going to be doing any vertical translations for the tangent and cotangent. And then you can just go halfway between and just plot another point. So, in other words, you're going to have, like, your 5 key points would be something like asymptote, asymptote, intersection, and then another point and another point. So that's the sort of the 5 key points that we're looking at there. So as far as how do you find the vertical asymptotes for the tangent and the cotangent, well, you have to consider for your mother function tangent curve, your asymptotes occur at negative pi over 2 and positive pi over 2. So what we can do is we can take this bx minus c, which affects the graph both horizontally, because one of them would affect the period, and one of them would affect the phase shift, the horizontal translation. And we'll set it equal to negative pi over 2, and we'll set it equal to pi over 2, and then we're going to get our new asymptotes. So in other words, you're going to say bx minus c equals negative pi over 2, and bx minus c is equal to positive pi over 2. And then for the cotangent curve, we have the asymptotes for, if we were looking at this first one, if we wanted to consider this one the mother function, we have asymptotes at 0 and pi. So we're going to say for the cotangent curve, let's let bx minus c equal 0 and bx minus c equal pi. So let's go back to that example where we're going to do a little bit of analysis. So we're not actually going to graph it, we're just going to do a bit of analysis. So first of all, let's talk about what the numbers that we see, the 2 and the negative 1. Do you have this one? Oh, I forgot to put this in your notes. Sorry about that. You can maybe fit it in the we're not going to write that much. What would the 2 do to the function? So a vertical stretch by 2. What about that negative 1? Yeah, it's going to go down 1. What do you think about the x over 3?
Horizontal stretch.
So that's going to affect the what?
The period.
It is going to affect the period. Now remember when we did the period with the sine and the cosine, it was 2 pi divided by b? Because our mother function had a period of 2 pi. Well, now we've got periods of just 1 pi. So this period is going to be
3 pi.
Pi divided by b. So pi divided by a third. Whoops, said pi, wrote b. So yeah, 3 pi. Okay, let's move on and do the one that we actually have to graph. I guess I could skip that one. All right, here we go. Number 2. We're going to sketch the graph of, did I give you this one?
Nope.
All right, so let's go through this technique here. We're going to find our vertical asymptotes. So we want to set the whatever is after, like inside the parentheses there after the tangent equal to negative pi over 2 and pi over 2, and we'll set up our t-table. So we'll have x over 2 equals negative pi over 2, And also x over 2 equals positive pi over 2. Solve for x. All right, so you should have got negative pi and pi. So then I'm going to make a t-table with 5 points. We'll put negative pi first and then pi last. We'll go halfway. So what's halfway between negative pi and pi? And then halfway between 0 and negative pi. So the first one and the last one, this is going to be where your asymptotes are. So those y values would actually be undefined. Since we don't have a vertical translation, that halfway 0 point, that's going to just be at the origin, right? It's not been shifted up or down, so it's going to cross at 0 on the axis, just the way the mother function does. The only thing that's really been changed here is what? From the mother function, what's been changed? The period. And if you wanted to, you could figure out that your period would be pi divided by a half, which is 2 pi, but you don't have to do that because you can see the distance between consecutive asymptotes is pi units. All right, and then we need to figure out what would the y coordinate be for negative pi over 2. Say again? Negative 1, yeah. And for positive pi over 2? 1. So one thing that you could do, and I do encourage you, hold on, I'm about to show you. I do encourage you to use your calculator. I'm going to clear out what I have. Make sure you're in radian mode. And we can just go to y equals and graph tangent of x over 2. And look at the table. Let me change my table settings to ask. So when I change my table settings to ask, I can confirm. If I type in negative pi, I get an error because it's trying to divide by 0, and that's undefined. If I do negative pi over 2, there's my negative 1, 0, pi over 2, and pi if you'd like. So that I definitely encourage you to use your calculator to help you. You can, of course, look at the graph of the function if you'd like. I'm just in my standard viewing window, and I'm in radian mode, so it looks kind of pretty, like it should. It's just been, the only thing that's changed is the horizontal stretch because the period has changed. So let's recreate that on our graph paper. You may want to, if you're going to use the grid lines, maybe you can go out. If you want every grid line to be like a quarter pi, or if you want every grid line to be a half a pi, however you want to do it, just as long as you label it. All right, let's go to talk about the cosecant functions. So I think I gave you this slide where I gave you the sine curve, but like dashed. So if you want to graph the, we're not going to do this, we are going to do this every single time. To graph the cosecant curve, you want to take every point on the sine curve and find its reciprocal, because that's the relationship between cosecant and sine. So, for example, if we go to the origin, that y-coordinate is 0. What would be the reciprocal of 0? Undefined. And what do we graph whenever it's undefined? An asymptote. So wherever the sine curve crosses the axis, we're going to have an asymptote. Okay. What about, let's go here to like pi over 2. The y-coordinate there is 1. And what's the reciprocal of 1? 1. That's nice. So we're still going to have this coordinate that's pi over 2 comma 1. And also at 3 pi over 2 comma negative 1, we're still going to have a point there. We can go over here to the left. Now here's where it gets a little bit crazy. So this is pi over 4, this little tick mark right here. So pi over 6 would be somewhere between 0 and pi over 4. And what is the sine of pi over 6? A half. So it looks like it's probably here, right? That looks like it might be a half. What's the reciprocal of a half? 2. So about here, if that's pi over 6, we have to go up to 2. You're also at a half, it looks like maybe about here, that's what, at 5 pi over 6? So at 5 pi over 6 there, we're also going to be up at 2. And you could plot more points if you want, but you're going to get the general idea of the shape here. It's actually not a parabola, but it kind of has that U shape to it. And then you're going to have the same thing happen here. This is negative a half, so that's going to go down, well, about here is negative a half, so it's going to go down to negative 2, and then there down to negative 2. So we're going to have another U shape, but opening downward. The main difference between this and a parabola is that a parabola does not have asymptotes. Parabolas are getting wider forever, and these are approaching these asymptotes. All right, so this is the graph of the mother function cosecant curve. What do we think about the period? Mm-mm. It's still 2 pi
Ooh.
because you have to have like one upward facing U branch and another downward facing one. So you still have to, the whole, all the way from 0 to 2 pi gives you one period. What do we think about amplitude? Just like the tangent and cotangent. There's none. There's no amplitude. You can, of course, have a vertical stretch or shrink, but you don't have an amplitude. All right, let's do the, but everywhere that the cosine curve crosses the x-axis, you're going to have an asymptote. 2 pi, so this time the period is going to be from, like one cycle is from the 0 to 2 pi, so you sort of like have half of an upward U, one complete down U, and then the other half of an upward U. So it's a little weird there. Just because it's the reciprocal of the cosine is high, medium, low, medium, high. And again, with the amplitude, there's no amplitude. All right, let's summarize some of that information here on this chart. So, domain of the cosecant function. So here is our cosecant function. What do we think about the domain? All real numbers not equal to n pi? Or 0 plus n pi? Yes. All real numbers not equal to n pi. The secant function. We can actually jump down and do the vertical asymptotes at this point, because the vertical asymptotes for the cosecant function would be x is equal to n pi. Make sure you write the x equals, because asymptotes are lines, and lines have equations. And then for the secant function, it's going to be x equals pi over 2 plus n pi. Let's talk about the range. They have the same range. Nailed it. So yeah, we have to go from negative infinity to negative 1, including the negative 1.
Union.
And then from 1 to infinity. Period is 2 pi. The cosecant is odd. The secant is even. So with the cosecant being odd, of course, it has a symmetry. If you rotate around, you get the same graph. But the secant does not have that symmetry, but it does have symmetry about the y-axis. So if you were to fold over, then you'd have the same graph there. All right. So I know I didn't give you the example. So if you want to go to your own paper or your graph paper, let's do a bit of analyzing the graph of this function. Now, I would say that the sine, the cosine, the secant, and the cosecant, I tend to use the same process for graphing, like as far as making your table of 5 points, amplitude, period, etc. It's the tangent and the cotangent that's a little different, where you take that bx minus c and set it equal to what your mother function asymptotes would be. So, of course, we don't have any amplitude, but we have something that's going on vertically. So what do we have?
Vertical float.
We have a vertical stretch.
And
So it's a vertical stretch by 2, and it's a reflection in the x-axis. Okay, so that takes care of the negative and the 2. What about that pi in front of the x?
that if you can
That affects the period. So the period is going to be it's still going to be 2 pi divided by b, or 2 pi divided by pi. So it's just 2. Phase shift, right 1.
right.
So your phase shift is still going to be c divided by b, just like for the sine and the cosine. where you have to ignore the negative. The c is just pi, and then the b is pi. So it's 1, and it's to the right because it's positive. And then it goes up 1. So that's your vertical translation. We're going to go up 1. How am I doing on time? 55? Okay, I got 10 minutes. Okay, cool. What do you need?
Do you have the sheets from the other day? Like my computer wasn't working, so I didn't get them out.
Okay, I'm not done. So, in a minute. Okay. So we can do the same. We're going to get into our. I think I just have one. Yeah, just have one more example. We're going to graph. But let me just go ahead and set up the t-table. We're not going to actually graph this one, but the t-table process will be the same thing that we do for the reciprocal of the secant would be the cosine. So be thinking about the cosine function when we set up our t-table. Now, sometimes what I do is I will set up what the cosine would be, and then I can have another one for what the secant would be. You can flip those columns if you want. All right, so for the cosine function, remember it goes from, normally it would go from high, middle, low, middle, high, but we do have this reflection in the x-axis, so what's this one going to do? Low, middle, high, middle, low. And again, thinking in terms of a cosine function, let's ignore the fact that it's a secant function. What would the y coordinate be at the low point?
Negative.
How about let's do the middle first, because the vertical translation is the middle. So the middle would be 1, right? And then is a vertical stretch by 2?
3.
Well, you're at 1, and you have to go down 2 from that.
Negative 1.
-1. So there and there. And then the high would be 3. Okay, we'll come back to the secant in a minute. Let's do the x. So we're going to do the same thing that we did with the sine and the cosine. Your phase shift is the starting point, so that's just going to be 1 to the right, positive 1. And then you're going to add the period to get the stopping point, 3. And halfway between 1 and 3 is 2. And then halfway is 1.5, 2.5. Okay, so that all makes sense for the cosine function, right? So remember, for the secant is the reciprocal of all of that. But you have to be careful because the reciprocal of 1 is a 1, but that's where you're going to have your asymptotes. The middle points are where you're going to have your asymptotes. So asymptote, asymptote. And it is still going to pass through the -1 and the 3 and the -1. So it'll actually, and we'll do this in just a minute, it'll actually look like this. So you're going to have, at 1, it's going to go down to -1, and then at 2, it goes up to 3. So if you can imagine that the cosine curve would look like this, right? It's got a vertical translation, so that would be like your midline. And so it's low, middle, high, middle, low. We just have to take this low point and so your asymptotes would be there at 1.5 and 2.5. You just have to sort of draw those half U things. Yeah, Claire?
Why is the high for the secant not 1/3?
Okay, that's, you have to be careful there because we shifted it up, you can't really follow those rules about doing the reciprocal. It really only works if you don't, the other thing is, like, when we were doing it here, we really only did the reciprocal bit of the values that were not part of our 5 key, right? The 5 key ones were like the middle, high, middle, low, middle for this one. So we were just looking at this point was the same, and then the low points are the same. So those we're not going to do the reciprocal of those. All right, let's do this last one. 2 cosecant of x plus pi over 4. All right, so we've got a vertical stretch by a factor of 2. The period is just going to be 2 pi. Phase shift, what do you got there for the phase shift? Well, which direction? Left. So you can say negative pi over 4. If you want to say to the left, you're actually being redundant, and that's fine, but you are going left. And then, of course, we don't have a vertical translation there. So if I set up my t-table, I'm going to do the reciprocal of cosecant is the sine. And I'm going to make another column for the cosecant. And we normally go for the sine, we normally go high, no, we don't. We normally go middle, high, middle, low, middle. So wherever it's the middle, those are where your asymptotes are going to be.
Is that for both cosecant?
Yeah,
and-
whenever you hit the middle, those are your asymptotes. Yep. All right, talk to me about the midline of the sine function. If this were a sine function, it would be 0. It's not going up and down at all. And it's a vertical stretch by 2. So how high would the sine function go? 2. And how low would it go? So those are going to be the same for the cosecant function. And then for the x, that's going to be your phase shift is where you start. So negative pi over 4 will be the first point. And then you're going to add your period to get the stopping point. 7 pi over 4. And here's where it gets real fun. You have to figure out how it's halfway between negative pi over 4 and 7 pi over 4. Halfway between 3 pi over 4 and negative pi over 4. 1 pi over 4. And then halfway between, you can start to see a pattern. You got negative 1, 1, 3, blank, 7, 5 pi over 4. So I tend to do this without any graph paper. I like to do it freehand. So I know I need to show out to 7 pi over 4 for my x. So we can just, if you want to look at it in your calculator, you can just do 2 divided by the sine of x plus pi over 4, because the sine and the cosecant are reciprocals. And then if you kind of want to make it look like your paper, you can go to your window and change your x min to maybe negative pi over 4, and your x max to 7 pi over 4. And you can leave the scale on 1 if you like. Or you can make your scale be pi over 4, and that's just going to give you a tick mark every pi over 4. And so now it looks like it does on my paper. I don't think I showed you guys this the other day, but when you're graphing something, if you go to the zoom, there's some preset zooms that are nice, like zoom trig. If you're in radian mode, so if you press that, it's going to default to having the x min will be negative 2 pi approximately, and then the x max will be 2 pi approximately, and then I think this is like negative 4 to 4. If you go to window, you can see what it is. It's not quite negative 2 pi, because negative 2 pi is negative 6.28 something, but it is negative 4 to 4 on the y. And then if you're graphing, if you're in degree mode, we're not going to be graphing in degree mode, but if you were, and you pressed zoom 7, zoom 7, and then you looked at your window, it takes you to almost negative 360 to positive 360. So it does recognize what mode you're in. But again, we're going to be graphing always in radians. And so zoom 7 is a nice standard viewing window to look at. But then you can always go in and change your window to whatever you'd like it to be.